from Rogani College of Engineering and Technology. Myself, I am Rajkumar, Assistant Professor, Department of Mechanical Engineering. In this video lecture, we are going to discuss about ideal and real gases. Pure substance is defined as a substance which means that it is homogeneous and unchanging in chemical composition. In composition of a gas mixture, that is mass and mole fractions. To determine the properties of a mixture, we need to know the composition of the mixture as well as the property of the individual components. There are two ways to describe the composition of a mixture, either by specifying the number of moles of each component called molar analysis, or by specifying the mass of each component called gravimetric analysis. PVT behavior of gas mixture is nothing but P means pressure, volume and temperature for ideal and real gases. An ideal gas is defined as a gas whose molecular are spaced far apart so that the behavior of a molecule is not influenced by the presence of other molecules situated encountered at low densities. It is also mentioned that real gases approximate this behavior closely when they are at a low pressure or high temperature relative to their critical point values. The pressure, volume, temperature, that is PVT behavior of an ideal gas is exposed by the simple relation PV equal to RT, which is called the ideal gas equation of state. The PVT behavior of real gas is expressed by more complex equations of state or by PV equal to ZRT, where Z is the compressibility factor. Then PVT behavior of gas mixture. The prediction of the PVT behavior of gas mixture is usually based on two models: Dalton law of partial pressure and Avogadro law of partial volumes. Ideal gases, that is a molecular, do not influenced by other molecules, that is low density, the low pressure or high temperature. The Dalton's law of additive pressure and Avogadro's law of additive volumes. Then first of all, we are going to see the Dalton law of partial pressure. The Dalton law, also called Dalton's law of partial pressures, state that the total pressure exerted by a gaseous mixture is equal to the sum of the partial pressure of each individual component in a gas mixture. The Emeryal law of observed by John Dalton in 1801 and is related to the ideal gas law. Mathematically, the pressure of a mixture of gas can be defined as the summation of Pi, that is P total equal to P1 plus P2 up to Pn, where P1, P2, Pn represent the partial pressure of each component. It is assumed that the gases do not react with each other. Avogadro law of partial volumes. The Avogadro law, or the law of partial volume of 1880, described the behavior and properties of mixture of ideal thermodynamics, that is as well as some cases of non-ideal gases of use in chemistry and thermodynamics. Avogadro law states the volume of the gas mixture is equal to the summation of volume Vi of the k component gases if the temperature T and the pressure P remains the same, that is volume of mass in the bracket temperature and pressure equal to summation of I equal to 1 into K in Vi into T comma P. This is the experimental expression of volume as an extensive quantity is the name after Emil Amat. Both Amat and Dalton law predict the properties of gas mixture. Their prediction are the same for ideal gases. However, for real gases, the result differ. No, Dalton law of partial pressure assumes that the gases in the mixture are non-interacting and gas independently apply its own pressure, the sum of which is the total pressure. The Avogadro law assumes that the volume of each component gas interaction of the different gases are the same as the average interaction of the component. Ideal gases. An ideal gas is the theoretical gas composed of a set of randomly moving point partials that interact only through elastic collision. The ideal gas concept is useful because it obeys the ideal gas law, a simple equation of state that amphibians to analysis under the statistical mechanics. At normal amphibian conditions such as standard temperature and pressure, most real gases behave qualitatively like the ideal gases. Generally, the deviation from an ideal gas tends to decrease with higher temperature and lower density as the work performed by intermolecular forces become less significant compared with the particular's kinematic energy, and the size of the molecule become less significant compared to the empty space between them. The ideal gas model tend to fall at lower temperature or higher pressure when intermolecular forces and molecular size become important. At some point of low temperature and high pressure, real gases undergoes a phase transition such as to liquid or a solid. The model of an ideal gas, however, does not describe or allow phase transition. These must be modeled by more complex equations of state. Real gas. Next, the ideal gas law is only an approximate to the actual behavior of gas at high density, that is at high pressure and low temperature. The behavior of actual or real divided from the predicted by the ideal gas law. In generally sufficiently low pressure or at low density, all gases behave like ideal gases. Real gases is an opposite to a perfect or ideal gas. Effect refer to an assumption based where the following are taken into account: compressibility effect, variable heat capacity, van der Waals forces, non-equilibrium thermodynamics effect is used with the molecular dispersion and element reaction with variable combustion. For most applications, real gases models have to be used near condensation point of gas, near critical point at very high pressure, and the several other less use of cases. This is the difference between the ideal gases versus real gases. The ideal gases are obey all gas law under all condition of the temperature and pressure. Real gases obey the law only the low pressure and high temperature. Then ideal gases are the volume occupied by the molecules is negligible as compared to the total volume accepted by the gas. The volume acceptable by the molecule is not negligible is compared to the total volume of the gas. In ideal gas, the force of attractive among the molecules are negligible. The force of attractive are not negligible at all temperature and pressure. Thank you.